Hello, my name is Chenhui. I'm from Tenstorrent. I'm very glad to present to you our Testbench code generation framework we named Jinko. Let's get started by a question. Why most of design and verification engineers prefer the generated code over the handwritten code? To answer this question, let's think of how we generally write a code to solve some problems. First, we need a logic to think of what's a good way, what's a plan, what's a good solution. Then we'll pick a good programming language or a good methodology to do an implementation. Then using that implementation to achieve our final functionality. However, during this process, we will make a lot of mistakes and also introduce a lot of bugs. To avoid this happen, we are trying to make the implementation stage as easy as possible. So a code generation system can generate most of the structured code to improve our code consistency and quality. So we make our functionality with generated code to be with less bug. So even we found bugs, using generated code can always help us quickly do a turnaround. So what's most importantly is using generated code can reduce most of the duplicated work in our working. And also using generated code can also increase our working efficiency because we don't need to do a lot of duplicated work. The traditional code generation methodology is based on code macron or code templates. The basic idea is we insert the design-related metadata or some customized target data into our template. However, there's a challenge for the traditional code generation method. First of all, as the design and the corresponding verification collateral become more and more complicated, we need to have and maintain an increasingly large volume of metadata. And also, this kind of a static generation approach seems not flexible, and also it's less extendable. Most importantly, the templates are deeply bound with some specific programming language or methodology. That's what causes a problem. For example, let's say we have a Testbench generation template for UVM. One day, our team wants to try something on validator, which requires a C++ Testbench environment. In that case, it will take a huge amount of effort to redevelop a new Testbench methodology for that. Although the internal Testbench logic may stay the same, and that wastes a lot of time and resources. So we developed a novel code generation framework. We named it Jinko. So why do we call it Jinko? Since it's a framework to generate code, it pronounced similar to Jinko tree. And internally, our data structure is based on a tree data structure. So that's the reason we call it Jinko. We use the Jinko framework to develop a UVM testbench generation flow called GenUVM. And GenUVM is a proof of concept using Jinko framework, and actually we can do more in the future. The GenUVM is the first application and the first proof of concept that we can use the Jinko framework to generate the code. The Jinko framework is coded using Python and has a SQL database facility to store the data for both design and verification. It also has a web GUI for user to use. The web GUI is based on the framework of popular package called Dango. So using the web GUI, even the engineer without any knowledge of Python can still use the Jinko to generate code for their testbench. So here is the Jinko procedures to generate a UVM testbench. From the RTL design to the generated testbench code, we should go through 3 phases in the Jinko framework: the collecting phase, the configuration phase, and the generating phase. I will talk more about this phase in detail in the next couple of slides. These phases can be configured with either Python script or through the web GUI. And all the data generated during these phases will be also stored in the SQL database. So first is the collecting phase. The purpose of this phase is to collect all the necessary information from the design. In first step, we will let RTL design to run 1 unit of timestamps to generate the FSDB. So in this step, there's no stimulus. So we simply instantiate the dot initial block, then run for 1 unit of timestamp. By doing that, we will have all the signal name and the signal hierarchy information stored in the database. Then, in the next step, we will use a tool to extract this information out from the FSDB and store them in the database. So all the information, all this signal hierarchy, signal name will be extracted from FSDB and then stored in a tabular format. And this data will be stored in the database for the next phase to use. So by doing this, we don't need any metadata or any collateral from the design. We can note all the information from the RTL file itself. So wherever the design change, we will always get the updated information from the design. So no matter how big or how complicated the design is, we can always get all the necessary information as long as this RTL design file can be compiled. So the whole tool chain makes this happen in our connection phase. Here's a sample of the design data uploaded into our database. We store this signal property in a tabular format in a SQL database, like what type of this signal it is, what's the hierarchy, what's the signal range. Then we will use a SHA function to generate a SHA tag for each signal. And this unique ID for each signal will be used for the next phase in the future. So next is the configuration phase. This phase is the most important phase in the Chenhui framework because in this phase, we need to configure what your test bench looks like. First is the signal mapping. In this signal mapping stage, we'll create verification signals and create and decide how do they connect with the real RTL signals. So in most of the case, this stage is done automatically. It will create a flat name for the verification signal from the RTL signal name, and then connect this verification signal direct to the RTL signal through the interface. Unless the RTL signal is too ugly to use, which normally we will not change the name, but unless the name is too ugly to use, we will still have a chance to customize the verification signal names here. And this verification signal will be used in our test bench. The next stage is the signal attribute configuration stage. So in this stage, we can configure the basic attributes for the verification signal, like give a hint to see if it's in the input or output, what kind of data type it is. And if you want to use it in a sequence item, will they be randomized? So this kind of attribute we decided at this stage. After that, based on the functionality of the different verification signals, we need to group them into different units. So in the Chenhui framework, this is the most basic element we use to build our test bench. So we call it component element here, CE. So based on the functionality of the signal, we group them into a component element. And this component element can be grouped again to become another component element to be used somewhere else in our test bench. The component element represents the components in the test bench, and they will have a type we call a component type, CE type, and component element type, which represents their functionality, like a driver, like a monitor, like a sequencer. We will talk more about that in next slide about CE type. So in the last stage, we will use the generated component element to build our dependency tree to represent our test bench. We will use this dependency tree to generate the test bench code in a correct sequence. In this slide, we will talk more about component element type in G-code. The CE type represents the functionality of that tree node, and each CE type will have one or more Python handler code. And this handler code will be used to generate the test bench code during the generating phase with correct order, using the information in that node and together with its child node. For example, a CE type of a sequence item will instantiate the verification signal, and the CE type of a sequencer will instantiate that sequence item and also generate all the necessary code for that sequencer. Let's see an example. To make it easy, let's say we want to generate a test bench for a tiny ALU with both stimulus and checker. We will have an interface in signals showing this graph, all the input, all the output, and all the control signal for that tiny ALU. The test bench dependency tree will be constructed from top to down like that on the right. First, we need a test bench top. Then we need a clock and reset interface and a package domain containing all the other test bench components. Under the package code, the package node will have an environment containing two agents, one's the input, one's the output, and the one checker component. So this is not all the tree. That's not the end of the whole tree. If we expand one of the agent node, we can see more detail what's under that node. We can see a driver, a sequencer, a monitor component. That's how we construct dependent tree for our UVM test bench. The reason of using tree is the tree data structure can be used easily to represent our test bench structure. So every parent node can be generated only after all its child nodes are known and created. Let's see example. In this picture, we can only create a driver node only after we know all the information for its child node, the sequence item, and the corresponding interface. Only we create all the child node for the driver, then we can generate a code for that driver. So the tree data structure can perfectly represent that dependency. So in the generating phase, we will use the post-order traversal algorithm to doing that, to generate a whole test bench in a correct order. So in the generation phase, based on different CE type and its handler code, the G-code can use the information in the database to generate different kinds of products, more than a UVM test bench. It can generate a C++ test bench, as long as we implement the handler code for C++. While the internal test bench logic stay the same, we don't need to develop a new test bench methodology, a new test bench structure. We just need to change the handler code. That's a new test bench. Furthermore, we can use it to generate more than test bench. We can even use it to generate a document. We can even generate for coverage, right, with corresponding C handler code. So why we use a database in our code generation framework? The main reason is we are trying to separate the data from the logic and implementation, so that we can make our framework independent of any programming language or methodology. By using database, the data of the test bench design can be remembered and can be reused and shared. So that gives another advantage is it provides a foundation Like, because we stored all the data and give a foundation for the future, if we want to do a data mining for this data, apply a machine learning algorithm to generate a TV. It provides a foundation for that. And of course, the SQL API is an industry standard language to access data. So it helps a lot because it's a lot of popular language like Python or C++ already has a lot of useful modules for these APIs. And it also reduces a lot of our development cycles when we develop this Jinko framework. So Jinko is a code generation framework based on tree structure. It is independent of language and methodology, so it can be applied to most of the use cases in our industry. Using Jinko for a Testbench code generation, we don't need to maintain and manage any metadata or any template libraries, which make it super easy for us to regenerate the whole Testbench when the design change during the execution stage. And of course, we can use the Jinko to generate a modern Testbench, like as I said, the document and the coverage, or even the debug facilities. There are still some constraints for Jinko. For now, it cannot provide a very meaningful and complicated sequence. The stimulus side, the stimulus still needs the input from the design verification engineer. And in the future, we hope to enhance the Jinko framework in this side. We are looking into the portable test and the stimulus library PSS and hope that will help. Secondly, of course, this framework requires some learning curve for most of design and DV engineer. They need to know a lot of CS background to use that. So we were trying to make that easy for most people to use. So in conclusion, Tenstorrent has successfully used Jinko to build a floor to generate a UVM test bench. So this floor has been used to create a test bench for various subunits of a high-performance RISC-V CPU project. And we use this test bench methodology, generation methodology, during our bring up process. It's really helpful and speed up our cycle for doing the bring up process for our project. In the future, we will make more effort to develop different kind of a C handler code to extend the Jinko usage to generate more than a UVM test bench. Also, we will enhance our sequence library to support it to generate more meaningful stimulus. That will be the goal. Last but most importantly, since we store all the data, design and test bench data in our database, and we have enough data to be trained, that means it will become a foundation to apply some machine learning algorithm to our test bench generation. So in the future, we hope we can apply AI to our test bench generation methodology, which means we want to use AI to generate the test bench in a completely automatic way. So that's our goal. Thank you for listening.